So, hello everyone. As I said, I'm Greg Cohen. I'm from the International Centre for Neuromorphic Systems down in Sydney, Australia. So I'm from the Western Sydney University, and today I'm going to give you a bit of a sense of some of the work we do because I think it's particularly interesting to this effort to create some sort of standardization because we do a lot of applications. We really go after solving actual problems and using event-based sensors as a core technology in tackling an existing problem. And you can see from my title, there's quite a range of things. I'll explain why robotic foosball is interesting and why it's relevant to how we collect data. And we also do some really interesting things using event-based cameras in space, both in space and looking at space. So, it's a bit of a wide field, but I'll use them as examples to explain why I think there's some things we have to be very careful about when we decide how to store data, how to share data, and exactly how we process data. So just to give you a little bit of background of who we are, the International Centre for Neuromorphic Systems is a relatively large neuromorphic research group in Australia. It's definitely the largest in Australia. There's about 60 people in total. And we essentially focus on three mainstreams: neuromorphic sensors. So we build our own sensors, both event-based vision sensors, audio sensors, tactile sensors, even electronic noses as well. So we like to build the sensor hardware as well when we can. We also look at processors. So we have our own neuromorphic processor, and we like to work with other ones as well. The idea being, you want to be able to process these neuromorphic sensors in this sort of paradigm which they're presented. And then we have a lot of work in algorithms, which essentially tie those two together. And I think what gives us a lot of direction is that we have very strong applications that we drive our design towards. So once you start out with a specific problem you want to solve, the choice of sensor, the choice of the processor used, and the algorithms all have inherent definition in terms of what you need to do and constraints that are applied upon that. And that really gives us an advantage in making decisions because we know exactly what we need our sensors to do, and we know exactly what our processes have to run on and in the environments they have to run. So just to go, to a bit of theory and a bit of sort of our approach to sensing, and I spent quite a bit of time thinking about what makes neuromorphic sensing different from conventional sensing. I think this slide sums it up quite nicely. Normally, when we do conventional sensing, we're doing uniform sampling in time. We divide time up into regions. We sample at a frame rate or a sample rate, and that's great because you get exactly the amount of data you expect at exactly the moments you expect them to be. The problem, of course, is that you do miss things between your samples, and you don't get any more data. So, the faster you go, the more data you get. If you want to see something really fast, you have to capture a lot of data. You have no variability there. Neuromorphic sensing essentially changes that. We essentially do what I would call threshold sampling. So we divide the signal up into regions, and we only tell you when those regions are crossed. And that gives you a whole lot more time resolution, but it changes everything about how you sense because, as people before have said, you get activity-driven sensing, for example. And this is a very different paradigm to work in. Now, I think the next slide really brings home an important point, which I think people have touched on before as well, which is that there really are two different tasks you're trying to do when it comes to especially computer vision. One is the reconstruction task. I mean, that was what cameras were originally built for. Taking a photo was really a way to capture the scene in front of you so that you could fool your eye into seeing it later on. We don't know what your eye needs to, necessarily figure out who you're looking at or what you're taking an image of. So we try to grab as much as possible with the goal of doing a perfect reconstruction on that data. And that's a very lofty goal. If you don't know what you need to sense, you take everything, and that's the only way to do it. And there's lots of applications where you want a perfect reconstruction. And that's where I think conventional cameras do a fantastic job. The difference, though, is if you know what you're doing, you may not need all that data. If you know exactly what you're looking for, then the task becomes a decision-making task, and you only need to grab the data you need to make that decision. And I think that's where event-based cameras or neuromorphic sensors really have an advantage. It's in these tasks where you go, I only need to see this, therefore I'm only going to capture that small amount of data, and then I can make the decision that I want to make on that. And for some of the space tracking applications, I'll show you how useful that paradigm can be. But first, I'm going to just dive into some real data. Here's a recording from one of our buildings in Sydney. As you can see, it's some lightning, and what you're looking at the front is rain, and in the background, you can actually see the Blue Mountains. Now, I really like this recording because it's some of the research we do into lightning, and it turns out that neuromorphic cameras are absolutely fantastic for that. And the reason is that in order to look at lightning normally, you need to use something like a phantom camera. They're extremely heavy, they're extremely expensive, and the biggest problem is they can record for about 5 seconds before they fill up their memory. But with an event-based camera, if you just take that data and you render it at a slower rate, what you're seeing in the front is a piece of hail, and then you just get this spectacular view of the lightning as it sort of propagates across the sky. And to do this with an event-based camera, It generates quite a bit of data, but orders of magnitude less than the high-speed camera that you see at the bottom there. You can actually play this back at 1,000,000 frames a second. Yeah, lightning is, if you want to watch 19 minutes of lightning, propagate across the sky, you can. But there's two important factors here. The first one is that the phantom camera would have to sample every black pixel here 1,000,000 times a second to get the same amount of information. What we're seeing here is just the changes, which are the edges of the lightning strike and the rain and the pieces of hail falling in the foreground. Now, the important thing about this task is that the entire lightning strike takes place in milliseconds. So for this data, if you set your time resolution too large, so if you only care about milliseconds, you won't even see this. In fact, if you make a video of this at any reasonable frame rate, even 200 frames a second, you basically don't see the lightning strike. Or you can't really pull it apart. It just looks like a single frame. So when it comes to event-based data, there are some recordings I'll show you where everything happens in a couple of milliseconds, and there are some recordings where it takes 4 hours for you to see something. And that's a real challenge with event-based data. I think one of my colleagues said it really well, which is that I think Twitter gets on average about 500 million tweets a day. And in some of the recordings I'll show you now, we have that number of events in one recording. And that's an incredibly complicated computer information processing problem. So another bit of data I'll show you is actually a lunar eclipse from a couple of years ago. Here you're looking at the moon. I like this example because it shows up the high dynamic range of the camera. What you're looking at across the moon there is the line of the eclipse. Everything above that is illuminated by the sun. Everything below that is in shadow. And as you can see, we can see features on both sides of that line, which is something you can't do with a camera that has a fixed exposure time. So in this case, the fact that we have this high dynamic range essentially per pixel, and the pixels don't affect one another in terms of what they can see, gives you this really stark result. But without knowing what you were looking at here, you would have no idea what this data means. So part of the problem we also have with data is that the context in which you take this data is extremely important. The same thing here is that the motion in which we're moving the camera here, and the reason we had to move it was to keep the moon in the field of view because it's quite large. Obviously, it moves. And as a result of that, that's information that's really important to interpreting what you're seeing over here. The next thing I'll show you is a rocket launch. This is actually from the northern parts of Australia. This is an event-based camera pointed at a NASA sounding rocket being launched from the Northern Territory, the conventional camera on the right-hand side. And this is a good comparison because you'll see that the conventional camera just saturates. And then at that point, it's not very useful. Whereas with the event-based camera, you get an enormous amount of detail in the whole rocket plume right through the launch. And this is the example where you probably have enough events in here that's equivalent to the number of tweets that Twitter has to process every day. And we have to do that to make any sense of this. And there is tons of information here that you really want to pull out. Now, this is a particularly interesting example for us because here you have a hugely energetic event. You get an enormous amount of events, and playing it back really slowly helps here. Now, for the second launch that we filmed with this one, we actually had a camera in the exclusion zone on the ground pointed upwards. And that camera had to essentially sit there while they delayed the rocket launch for about 3 hours. So all it was doing was sitting on the ground, pointed up and recording the sky. So you don't often see a time lapse of event-based data, but here is one. And what you're looking at is the event rate on the logarithmic axis. Those bumps in the event rate, there are actually the clouds coming through and you can see the stars moving. But in this recording, most of the time we're playing it back 300 times real time, but occasionally something interesting happens and we really want to slow it down, go deep into the data, play it back slowly, and you'll see an interesting event that occurs. So the point here is you have all the benefits of the high-speed camera on all the time, but when something does happen, you have this shooting star coming to the field of view. A tiny event rate, something that if you filtered, because you're expecting the large event that's going to happen in a second when the rocket actually launches, you'd absolutely lose. So you have to be careful because the data can have both very fast, very high energy effects and very fast, very quick events as well. So yeah, when we play it back, you'll see in a second on that data rate, which is on a logarithmic axis, you'll see this enormous jump coming up, which is actually the rocket launch over there. But we just slow it down for that. And the point here is you don't have to trigger the sensor. But also at the same time, how do you deal with a file where you have these two phenomena in the same file at the same time? And, with this sort of recording, we just get this enormous amount of events over here. And you can, again, see the rocket move in sort of a very fantastically interesting trajectory through clouds and smoke, and we can observe it the whole way, which is really nice. This is actually a really interesting application because launch monitoring is a particularly interesting field. You don't think about it, but if you're launching a rocket and you have to get it insured, you want insurance companies to pay attention. And, there are reasons why they'd want to know what's happening with the rocket if something goes wrong. Again, with the example I showed of the cameras for lightning, we do a lot of lightning research from the ground and from space. And simply put, you cannot put a phantom camera in space. It's too heavy, it's too expensive, and it uses too much power. But you can, and we have put neuromorphic sensors in space to do the same task. And that's where things get particularly interesting. Before I get to space, though, I'll talk about the Astros Site, which is probably our most advanced neuromorphic product and something I think is important because it generates an enormous amount of event-based data every day. And the Astros Site is actually a neuromorphic product we built to tackle an interesting problem called space situational awareness. Essentially, space situational awareness is tracking the objects in orbit around Earth. And it's a big problem because we actually don't know how much is up there. We don't know where they are all the time. And everything we launch into space increases the risk of collision between satellites we launch, crewed spacecraft. In fact, they move the ISS every year to avoid space junk. And before we can even figure out how to start solving that problem, before we can legislate or clean it up, we have to know where everything is. So tracking these objects is a particularly important task. And actually, neuromorphic sensors are fantastic at this. It's the perfect application for an event-based camera. So this is where we started with the old ATIS sensor. On the left, you see the first satellite we ever caught with a camera and a telescope. It just flies to the field of view over there. And this is where we are now, which is when we have the telescope moving to track an object, the one in the yellow circle over there. And we track all the stars. We figure out where we're looking based on the stars alone. And we give you that position of that satellite thousands of times a second. So here we're using the event-based data. You can see it's a fantastically sparse scene. And normally you can't see the stars and the object at the same time. But because we use the high temporal resolution of the sensor, we can do both. And we can use that data to actively tell where that object is. Most systems that use telescopes to do this, they report the position maybe 3 times across the sky. We report the position thousands of times a second. And from that stream of events from that object, we can actually tell a whole lot about what's going on over there. So what we did with this is we actually built into a real-world product. This is the Astros Site. It's a mobile telescope observatory built into a shipping container using neuromorphic technology. So essentially, because we're changing the sense at the back of those telescopes to a neuromorphic sensor, you can change the whole way you approach the sensing, right? We actually image whilst we move, while everyone else will keep the telescope stationary while they take images. And as a result of that, we're not sensitive to motion the same way. Normally, when you build a telescope, you're seeing concrete in the ground, you build a building, you get rid of every bit of vibration. We don't mind that. In fact, vibration and motion helps us. So we can build it into an unstable platform like a shipping container, where you can just put it on a track, move it around, and have it somewhere else. We work with these things together, so we synchronize them for ranging type tasks. And there again, it becomes important, as was mentioned earlier, to know exactly how to time synchronize these sensors so that you can figure out the range from known points on the ground. So we have 3 of these at the moment, and they operate every night. And we've on top of that, we can also use, as I said earlier, the events rate from those objects to do all sorts of interesting analysis of what we're looking at. We can actually even tell what materials the satellites are made of by looking at color ratios between 2 event-based sensors. We can tell if satellites are tumbling or if they've changed. And this is data you can't get if you integrate. Integration is great. You get more sensitivity. We'll never beat an integrating sensor for sensitivity. But you lose all the small changes when you integrate. And that's actually becoming really important in figuring out what these satellites are doing. So for the Astros Site, we actually developed a whole bunch of tools to run them. They're completely remotely operable, and they're completely autonomous as well. So they'll go and observe satellites every night. And the reason I'm showing this is just a view of the Astros Site and of the objects it's uploaded. But to give you a sense, we have somewhere between 25,000 and 70,000 neuromorphic recordings of satellites that we've taken with this. And there's a lot of data you have to store around that. So here's an example of what one observation looks like. There's the event-based data on the top left. On the right-hand side, you see an interesting plot that shows that data represented in a way that's much more useful for people who are interested in space tracking. But here we've done something interesting. We have to at some point convert the events that we take from the cameras from the XY coordinate frame of the camera to sky coordinates, right ascension and declination. So now we have a whole different kind of event-based data. Time, which is now UTC, right ascension and declination. And that's actually what other people want from us in order to incorporate into their systems. But that again, it's still the event-based data. It's still position and time on individual events coming out of the camera. And of course, alongside that, we have all this other sensor data we collect as well that all has to be time synchronized. So, this is a case where we actually have data and event-based data that we want to pass on to other people. And a format that is standard, is something that we would need in order to make that something where everyone can already understand the data we're getting. And I should say in our lab already, we use multiple different kinds of data formats simply because it's so hard to share data, collaborate with people, and find ways to process data that we ourselves have collected. So just to go to orbit now, we actually have some cameras on the International Space Station doing some really interesting things. With the first project we have this Falcon Neuro, which is on the space station at the moment. We're building the follow-on, Falcon Odin, which will go up at the end of next year. And essentially the cameras are on the Columbus module. One looks directly down at Earth. It does this Earth imaging application. The other one looks at the RAM direction, which is sort of in the direction of motion of the ISS, as if you were looking at the front windshield as it was moving towards the horizon. So this is actually the first data we got from space. This is a strip of data rendered over Honduras, and it's really been fantastic. The mission here was to look for lightning and sprites from orbit. We see a whole lot of lightning, but also on top of that, we see a whole lot more information than we ever thought. But if you think about this, this is a really extreme environment. You know, I love the HDFI file format because it is easy to understand what's going on in there, but we don't have the processing or the bandwidth to do that on space. We have to find very different ways to get this data down from space effectively because, you know, it's a very challenging and expensive task to get data down from orbit. So we're designing sensors that capture data specifically in the sparse way to send it back to Earth. Here's another recording just over China of some lightning and some boats, just to show you the sort of thing you can see. This is an old Davis 240C sensor, so we only have 240 by 100 pixel resolution. And even with this, you can see spectacular lightning strikes, and you can see really small features because we're actually leveraging the motion here. And this data is really fantastic, and you know we have quite a lot of it as well. But there's a lot of other information you need around this, and I'll show you why it's actually quite hard to tell what's in these recordings. And I think the most interesting one I'm going to show you is from the RAM camera. So this is the one looking forward at the limb of the Earth. This is a recording from February. This is 30 seconds of data. It's about 1 megabyte. And when you look at this recording first, and when we first looked at this, we thought this was just noise. There's a bit of structure somewhere towards the middle at the bottom over there. But we honestly didn't pay this much attention until we started figuring out how to process it. And the really interesting thing here is that if you don't know what's in your data, you just essentially discard it. When you do a bit of processing, this is all post-process, you'll see there's a whole lot going on in here. I'm just playing the recording backwards and forwards because it helps you see things, but you can start seeing the geometry of the scene. You can see the horizon, you can see the stars going up and down, you can see the Earth features moving towards us, and you can see something moving from right to left, which is another satellite. And the point is that you might just discard that data initially if you didn't know there was so much in it, and that's almost what we did. And once you do know that data's there, you can start processing it. But if you start running noise filters, or you start using lossy compression on the raw data, you lose stuff that you didn't even know was there. And that's a really interesting problem because even if you simulate this data, and we did a lot of simulations of what we thought the data from orbit would look like, we can only simulate for what we know, not the stuff we don't expect. So if we filter preemptively based on what we think is going to be in there, we may very well lose the actual signal we care about. Because in this recording, there's actually a lot of stars, enough to do an astrometric fit and figure out where we're looking. And there's actually 5 satellites, all in 1 megabyte of data. So there again, you know, we would never have known this had we filtered this preemptively. So we always tend to say, unless you know exactly what you're doing and what you want, you need to understand that filtering your data can be disastrous because what looks like noise to you, if you know how you're moving the sensor, may actually be really important. And this is just a collection of recordings from the last couple of weeks from the ISS. And what you might notice is like the top one on the left looks completely different from the one on the right. Same cameras, same data processing pipeline. One is just looking down and one is looking at the horizon. And without the context of how you're moving and the camera you're actually using, even though this all belongs to the same data set, you can see it's really difficult to understand what's happening in this data. So again, I think the context around the data is just as important as the data sometimes, especially if you need to know how to process it. So quickly, I've only got a few minutes. I'll talk very quickly about foosball and pinball. This was something that came out of Telluride. We often play foosball there. So one year we thought, let's automate it. So we built a robotic foosball table and we set it as a challenge task for people to come and say, well, you know, everyone says we're good at tracking. Yeah, actually try track something. It turns out to be a really hard problem. But the reason this is so interesting to us is that data sets are fantastic, but they don't capture everything about a problem. Here, you really want to respond to what you're seeing in real time, and that's a much more difficult thing to capture in a static data set. So we do need these dynamic data sets, these dynamic benchmarking systems. So just as important as to find a good way to store the data, is also a very good way to, there's also a very strong need to figure out how to process the data efficiently and quickly as well. So we started with this and we moved on to a robotic pinball machine because this is actually a much neater problem. Here we actually have a very simple input system. You have 2 buttons to press. So you have 2 inputs left and right. And the most important thing about the pinball machine is that you have time. If you're not fast enough, you lose. There's no 2 cents about it. It's a real world problem with time constraints. Also, it has a score, which means that you can compare different systems. You can compare different cameras because ultimately, if you get a higher score, you're better in pinball. There's no other way to say it. And once you have this fixed marker in the sand to compare systems, you can use that to start figuring out, well, how about if I take the score and divide it by the power consumption? Now I've got a measure of how power efficient I am at the task of pinball. So these little toy problems like this are the way we define tasks. And the way we define tasks are really going to decide how we can compare performance. And I think being able to figure out how to share this data and how to make this data accessible to people is really interesting. So it works kind of well. as even with simple networks. But this is an open challenge problem that we like to share with people, and we'd love to figure out how to share both the data and the way to interact with this as well. This is just a slide I can send to people. We just started looking at different types of data sets at one point, between essentially open loop and closed loop data sets, and there's some interesting ideas why you might want closed loop data sets. I should just say, however, as my last slide, what I really think is important is that tools drive the adoption of file formats. We use a lot of file formats, but we tend to settle on a whole bunch designed by someone in our lab called Alexander Massaro, who has his own file format and a whole bunch of really useful tools in order to work with them. And because of those tools, the adoption of this file format in our lab is almost universal. And it's fantastic because we've now built our own tools to work around it. It's not the most efficient file format. In fact, Alex has come up with a better and more interesting file format that he's using in a project called Under, which we can talk about, which is just a way to make data accessible. But really, without the right tools, without the easy way to load data, without any concerns about what you're loading, file formats don't survive, I don't think, especially for us. So that's why I have such an interest in what we're doing here today. So with that, I'll leave it all. Also, my university always asked me to show we do have a master's degree in neuromorphic engineering if anyone's interested, and you get to play with space stuff and space technology. So with that, thank you so much and have a great day.